Hi, my name is Jaden Kwong, and this is my Lab 1 constant velocity. Okay, so just to briefly go over the report, we start off with the introduction, introducing the purpose of our lab. We'll go to our formulas and models that we used throughout our experiment, and then we'll go into our procedures that we used, our actual measurements, and then we'll see how we use GlowScript to find the computational and theoretical models, and then we will conclude our results, compare the two experimental and computational models, and then we'll discuss any further questions after. So the purpose of this lab was to observe an object moving at a constant velocity, meaning no net force or changing directions. And then we would compare these two graphs that we get with that of the theoretical and computational model. So starting off with Newton's first law, we reference this throughout our lab, and what basically it states is that if there's no net force, then an object in motion will stay in motion, or an object at rest will stay at rest. And then that also relates into Newton's second law, which relates acceleration with force and mass. And it states that acceleration is directly proportional to net force and inversely proportional to mass. And in simple terms, this means that the heavier an object is, the more force required to move or speed it up. And then this idea of constant velocity is used throughout our whole entire lab, meaning if net force is zero, and that means that there's no changing directions under constant velocity. Okay, so we start off with Newton's second law, and then we break down our change in momentum to our final and our initial momentum. And then we divide this whole entire thing by mass, and we get our velocity update formula. And then to find our position update formula, we use our average velocity, and we plug it into our position update formula. Okay, just to briefly overview the results, we took our experimental model here, and it looks fairly linear, so it looks as it supports the models as expected, but we will examine that further in the next few slides. Okay, so our object we used was our cart, meaning that was our system, and our surroundings are anything acting on the cart, which is things like friction or air resistance and maybe gravity. So using Tracker, we found the experimental position, and then we used GlowScript to find our computational model, and then we found our results using Excel spreadsheets. Okay, so we first recorded the cart moving with an iPhone camera, and then we analyzed the video in Tracker to find our position versus time graph that we saw earlier, and then we placed our initial conditions in the GlowScript, and then we built our theoretical model that we would use to compare in Excel to see if it supports the theoretical data. Okay, so in Tracker, this is what it kind of looked like. We used our meter stick to have a basis of our measurements and to certify our units. And then we set our origin and we set our direction of motion, and we started plotting points along that direction of motion to take measurements of our cart movement. So based on that movement, we got this graph again here. And then using this graph, we found initial position, our average velocity, and our total time. Okay, after that, we used all that information and plugged it into GlowScript right here, especially our initial position and our velocity. And then we used the frames per second from our tracker to find our delta t in our position update formula. So using our total time of the clip and knowing that net force equals zero, we used the position update formula to find the final position at the end of the entire clip, or our theoretical clip. So here, after building our theoretical model using GlowScript and our experimental model using Tracker, we find that our experimental model is very, very closely related and very linear, just like computational model, but it still has some sort of deviance from the computational model and is not entirely perfectly straight and linear. And that could be because of friction or especially air resistance. So these two forces are not accounted for in the theoretical model, as we assume zero friction or air resistance, but in the real world, friction and air resistance act upon the cart, possibly slowing down and making it not move at a constant velocity. Additionally, human error, like plotting the points in Tracker, could play a role in the deviance in the graphs. Okay, so what if the axes were flipped? They would have opposite signs, and the slope would switch to negative, and but the slope in the position versus time and the velocity time would still be constant still, even though the slope would be negative. And then our net force is going to still equal zero. And then we do not know how many pushes or pulls are being added together, but we just know that all the forces on the system all add to zero, and that does not necessarily mean that there are no forces being added. All right, thanks.